Hello, and welcome to the Heritage Science Academy webinar series of the IPERION Heritage Science Project and the European Research Infrastructure for Heritage Science. Thank you for joining us today in what has evidently been a very, very difficult period politically and in terms of the conflict on the continent. My name is Matija Strlič. I'm Heritage Science at UCL Institute for Sustainable Heritage and at University of Ljubljana. And I'm very pleased to be able to introduce to you the third webinar of the 2022 series of the HS Academy webinar series on the topic of remote sensing-based approaches for cultural heritage interpretation and monitoring. As usual, we will take questions at the end, so please do write your questions into the chat or into the Q&A function, but unfortunately, those questions and the discussion will not form part of the YouTube video. The speaker today is Dr. Nicola Masini, who's Research Director of CNR in Italy, and is also the Deputy Director of the CNR Institute of Heritage Science. He's Senior Lecturer at the Master's and PhD courses at the University of Basilicata in Italy, and his main scientific interests are focused on the development and application of remote sensing-based methods for archaeological research, landscape archaeology, cultural heritage risk analysis, and of course, conservation. Since 2008, he has been the director of the archaeological science mission Ithaca in Southern America. And he directed several international projects and scientific campaigns in Peru, China, Bolivia, Colombia, and of course, Italy. And for his services, he has received the President of International Fellowship Initiatives Awards in 2016 by Chinese Academy of Science. Many congratulations on that achievement, Nicola. Without further ado, I will hand over the screen to you. Thank you very much for joining us today, Nicola.
Thank you, Matthias. Good morning to everybody. Well, let me start this webinar with a thought, a heartfelt thought for the people of Ukraine who are living, experiencing the tragedy of the war that we are learning from the news, from the image of the destruction, and the satellite photos which tell us the military attack on Ukraine. Let me start with a consideration on cultural heritage science, on cultural heritage, which is not only the legacy of tangible and intangible heritage assets of a community inherited from past generation, but it is also a domain of study and research where multidisciplinary skills combine and contaminate each other, thus stimulating the development of new technologies and methods of analysis of research, which can be reapplied in other domains. Therefore, we can say that cultural heritage is increasingly a frontier area for development of some cases cutting-edge methodologies and technologies. Among the diverse imaging methodologies and technologies that in recent years have experienced an important growth in the field of cultural heritage, we highlight the domain of Earth observation, or more generally remote sensing, thanks also to the great development of increasingly performing sensor and platform. But what do we mean? What do we mean for Earth observation remote sensing? Earth observation is the gathering of information about the physical, chemical, and biological system of the planet Earth through remote sensing, which enable to acquire without making physical, without any contact with object of the land surface to be investigated, using spaceborne, airborne based sensor which can be passive. I mean the sensor which get the radiation emitted or reflected by an object, by a land surface, or active, typically the radar, SAR, LiDAR, which emit radiation directed towards the target to be investigated. This radiation is reflected from the target and detected and measured by this sensor. What do we observe from above? Well, for observation, we mean interpretation process. Well, we observe landscape revealing marks or indicator of the presence of buried archaeological sites. We observe landscape revealing patterns and traces of the past, sometimes traces which change their function over time, but are still preserved, as in the case of, for example, the roads which follow ancient Roman land division that we can find in a lot of regions of Europe, including in Croatia, here in showed, or urban landscape revealing evidences of ancient archaeological remains, as typically the city walls of our old historical center. In this case, I show the Ming Dynasty city wall of Kaifeng in China, very well preserved. As for the other many imaging techniques, also for remote sensing, sometimes there are some expectations that are overlooked for various reasons, especially when these techniques are used in operational context. The result is, we can say, the intersection between the potential, the practice, and the expectation. This is due to a number of reasons, such as the lack of dialogue between scientist and user, no? The technologist, scientist, and the archaeologist, conservator, and I don't know, the architects of which work in the field of restoration. Due to interpretation issue, because remote sensing, as other imaging technologies, provides only indirect data to be interpreted, is due to non-shared decision in the choice, for example, of the methodologies to be used for a given application. And also because sometimes we forget that F observation, the same consideration as for other techniques, is not the aim, is the mean. The mean of our that help us in providing information for the interpretation, monitoring, conservation of cultural heritage. So how bridge this gap? Bridge this gap, improving the access to F observation data. And well, in this case, we are doing a lot for this process of democratization of F observation data, making more and more operational remote sensing for the diverse use, from the preventive archaeology to the risk analysis and mitigation, up to the monitoring, the observation, archaeological disturbance, and finally improving the performance of technologies and making more robust the scientific methodologies. These are the three important challenges. About the first, the democratization of satellite data. Well, now we are lucky to have Google Earth. Google Earth Engine, which democratized the process of monitoring over large areas, and also the policy, the free, full, and open data policy adopted for by the Copernicus program of European Space Agency, which also developed a family of missions called Sentinels, each one based on a constellation of 2 satellites to fulfill receipt and coverage requirements, providing a robust data set for the diverse Copernicus services. So we are in presence of a large amount of data, big data, which are both resources and tools, which pose big challenges and offer big opportunities, thus opening new research frontiers, enabling innovative application with unprecedented value also for digital cultural heritage. The large amount of data and the variety of information makes it necessary to use automatic and semi-automatic procedure to use in artificial intelligence for extracting useful information on feature patterns of interest for the diverse application in the field of cultural heritage. Let's start as operational scenarios from the non-invasive preventive archaeology, which could be performed with the diverse approach, including the recognition and interpretation of archaeological proxy indicator, the enhancement of remote sensing data, the elaboration of multi-temporal data sets, Google Earth Engine, the integration of diverse remote sensing, including geophysics and the other close-range sensing or in situ analysis, and finally, automatic feature extraction. What do we mean for proxy indicator? Proxy indicator are indicator which suggest, which help us in detecting areas of archaeological interest. And to understand how detect this indicator, it is important to analyze, to understand the entire degradation process, starting from the abandonment of the monuments up to the ruin, up to the process of natural burial in subsoil, and in the subsoil, a physical interaction between remains, buried remains and soil produce a change in moisture content, in vegetation and growth of vegetation, in soil nutrients, which are visible from above, from an aircraft, from a satellite platform, through some marks, better known as crop marks, dump marks, soil marks, or shadow marks. And in some cases, help us not only in detecting area of archaeological interest, but also understand the typology of archaeological feature. No, for example, Roman villa and Neolithic settlements. I don't know, a fortified structure. Among the proxy indicator, the microtopographical, the microtopography are the most widespread and common, that can be observed from with using different remote sensing techniques, including remote sensing data, including optical, multispectral optical, LiDAR, SAR. But in this case, the proxy indicator can be from optical as shadow marks, LiDAR as microtopographical variation, and using the SAR, we can exploit the radar backscattering. The discriminability of archaeological crop marks is a complex issue because are linked to very subtle signals only evident in specific surface condition, vegetation type, phenology, moisture content, that can be captured, can be better captured, exploited the spectral resolution of remote sensing data, along with a number of statistical analysis of spectral indices, here shown on the right. That for sake of brevity, I cannot explain. But anyway, in this way, we can enhance the visibility of this proxy indicator. This surface condition, which the visibility of archaeological proxy indicator depend on, are not permanent. This times makes it necessary the use of more data, of multi-temporal data processing, inter-years, as done, for example, for Machu Picchu on the right of the slide, or intra-year, to analyze, to understand the seasonal variation of this proxy indicator, as showed on the left for Neolithic settlements in Apulia in the south of Italy. So big data analysis, it is a big opportunity. Big opportunity because especially when the geometric, the spatial resolution is not enough to detect using a single image a large number of archaeological features. Exploiting, processing a huge data set, for example, using Google Earth Engine. Google Earth Engine is a catalog of satellite imagery and geospatial data sets that makes available for everyone, which allow us to detect change, map trends, quantify differences on Earth's surface. In some cases, for this project, allowed us to detect unknown road section of the famous Appian Way, the Via Appia, which connect Rome to Brindisi, the most famous Roman road. Combining, processing more than 700 of images over 4 years. The approach is based on the identification on the basis of archaeological records and other ancillary data. Identify 2 classes of data of a feature, one related to area of interest, of archaeological interest, where road sections are expected, and the other one related to non-area of interest, where the Via Appia, Appian Way is not expected. So using Google Earth Engine, the spectral signature of the 2 classes was calculated over the entire multi-temporal data set, enabling the identification of the spectral bands characterized by a significant spectral distance, identification of the spectral band, and the data characterized by significant spectral distance between the 2 classes. And so in this way, we use the best image for detection of road section of unknown or buried road section of the Appian Way. It is just an application of big data analysis using Google Earth Engine. Another approach is the typical integration, qualitative integration of diverse remote sensing techniques, including geophysics. According a multi-scale approach, including satellite data, aerial data, UAV imagery, and geophysics, which allow us not only to discover larger settlements, large archaeological settlements, but also a small archaeological feature, such as a tomb, as in the case of this ritual offering of Nazca culture, for which we use satellite data and geophysical data, including georadar and geomagnetometry, which help us in the identification of an area that has been excavated by archaeologists, unearthing a rich archaeological record, including ceramic, textile, and music instruments typical of the Nazca culture in South Peru. Regarding satellite data, regarding generally remote sensing image, another approach is the typical enhancement of the data to facilitate the visual interpretation, using diverse way to visualize the band, the multispectral band, or using some filtering. In some cases, they don't change the original value of the reflectance of the radiation. In other case, change the value of the digital number of the pixel, such as the filtering, convolution, principal component analysis, and image fusion. Just to show an application, a simple application, for the Nazca lines, which are a cultural expression of Nazca civilization, which is very difficult to discriminate, also by using a drone. Well, exploiting some filtering, such as the directional convolution, it is more easy to discriminate and distinguish them with respect to other marks related to vandalism traces or other traces related to hydrological events. About the technological challenge and the effort that we have to produce to make these technologies more useful, more effective for archaeological application. But LiDAR represents probably a revolution, represented revolution in archaeological prospection in the last 2 decades, because with LiDAR it is possible to filter vegetation, to obtain a very high resolution digital terrain model, facilitating the identification of microtopography of archaeological interest. As in the case of this medieval site in south of Italy, which enabled to discover an unknown historical fortified site, but in this application we also applied a machine learning based approach, or automatic feature extraction approach, in order to identify in automatic way feature of archaeological interest. In this case has been compared with the interpretation with the traditional methods used by archaeologists, with a very important good results in terms of rate of success of the extraction of archaeological feature. Well, in this case, the LiDAR-based study allowed us to reconstruct the original historical landscape, but exploiting using a large data sets of historical data, archaeological record available. Well, changing scenarios, changing operational scenarios for use of remote sensing. As regards the risk, today we rely on a lot of satellite data, including the Sentinels, Landsat, MODIS, and which can be applied, used for different study, for different risk hazard studies, from the floods caused by extreme hydrometeorological events to biological chemical degradation, using, for example, Sentinel-5, but with a low resolution, structural movement using active data, SAR data, up to fire forecasting and monitoring. Here you can see an application of an area characterized by a rich archaeological heritage in the Ionian coast, famous. It is named the Great Greece because it was founded by Greek colonies between 7th–6th century BC. Well, this area is affected by diverse hazard, diverse problem, from the coastal flooding to erosion, and using using particular large multi-temporal data sets and exploiting diverse indices. From vegetation indices to indices which measure in indirect way the moisture content or the water content of land surface. It was possible in this case to map to obtain a flooded classification of this area, characterized by a lot of archaeological sites. Here you can see the algorithm used for this application. This area is characterized by multi-risk scenarios because include also the problem of fires. Remaining to the topic of the risk, SAR interferometry, a difference interferometry. It is a mature tool for measuring, monitoring ground motion, displacement of architectural structure. The method use 2 or more SAR image. SAR is acronym of synthetic aperture radar, which allows to generate maps of surface deformation, digital elevation, using differences in phase of the wave, which return to the SAR platform. It could be satellite or aircraft. So, interferometric capabilities allow to obtain very accurate, with millimetric accuracy, accurate displacement, as in the case of this application in the historical center of Rome, where exploiting Cosmos SkyMed data, it was possible to map, to identify some trends of ground motion and the displacement of the most important monuments in the historical center of Rome, including the archaeological area, such as Aurelian Walls, Colosseum, and other archaeological structure. Another risk scenario is related to the looting. The looting is a big problem which affects archaeological heritage that has material and cultural consequences, because it produces a loss of a work of art, as resources, but also a loss of source of historical archaeological information. The way to face this big problem, it is important to use a specific measure to contrast this phenomenon, which is a criminal phenomenon, from the selling to the transport to the collect demand up to the surveillance of looting using remote sensing. In some cases, it is important to develop appropriate techniques for the automatic extraction in those regions where it is not possible to conduct direct surveillance, as Syria, for example, or inaccessible regions of other countries, for example, in Peru, and exploiting developing an automatic procedure based on the use of local spatial indicator, unsupervised classification and segmentation. Well, we developed a method, a tool for extracting the looting feature related to pits or craters produced by the grave robbers. This is a map, the results obtained in Dureropos in Syria. It is important, of course, to integrate, to complement satellite data and the derived products of satellite data with other close range sensing methods, including drone, including GPR, ground penetrating radar, capable to verify, to measure the depths reached by the grave robbers, in some cases to verify the state of conservation by the remains, because in some cases the grave robbers was not so efficient, effective in finding the archaeological treasure expected. So, as a future perspective, well, one of these is to push in the development of close range sensing methodologies based on the use of drone. And with this regard, CNR, in the context of the platform E-RIHS, we are developing a UAV platform, a multi-sensor platform on drone, including multispectral, hyperspectral, thermal imagery, LiDAR, georadar, and magnetic, in order to conduct multi-scale investigation or multi-scale research project for diverse environmental conditions. Another important opportunity and perspective is to develop a platform, multi-scale platform for the environmental and microclimate monitoring of cultural heritage. This is an application conducted on medieval churches in Matera and other sites of south of Italy, based on three different monitoring systems: microscale monitoring system, mesoscale, and macro scale monitoring system, exploiting also satellite data. About well, more specifically, close range close sensing imaging techniques. Another important opportunity is to push in the development of multimodal machine learning based methods for the extraction of decay patterns of architectural surfaces or wall paintings using georadar prospection at high frequency, multitemporal infrared thermography. But in this case, we can also use other kind of imaging techniques, such as those used by Jana Striova, for example. So we have to push in the direction to integrate, to develop image fusion methods. And finally, a big opportunity is to try to develop a digital twin of cultural heritage. As I show a recent application, and with this application, I conclude my presentation, which is related to a European project conducted in Portugal. Well, where we selected a case study in Portugal, the famous convent of Carmo in Lisbon. In this way, we use different close-range sensing methods, technologies, from drone to GPR at high frequency, infrared thermography, sonic methods of investigation. And well, this is only the first step of this path. In the future, it is important to create this intelligent system of monitoring using also a sensor which measure displacement, environmental microclimate parameters, in order to create this system to support decision for cultural heritage conservation and the management. So in conclusion, we can say that Earth observation sciences and technology are major tools to be used for diverse application, from the site discovery to risk monitoring and documentation. The crucial issue remain the access to data and the interpretation. To facilitate them, it is important to improve, to propose, to favor multi-scale approach, including remote and in situ sensing, in the context of interdisciplinary project, which proved to be effective. Other potential to develop are the active remote sensing data, LiDAR and SAR, and intelligence, artificial intelligence for the automatic extraction of feature and patterns of cultural heritage interest, and big data analysis. The future challenges and opportunities, I think, are the digital twin that can be very important tools as decision support system for cultural heritage management, but also for the study of human past. Thank you for your attention. And I conclude with this slide.
Thank you. Thank you very much, Nicola. You've taken us through this amazing and stunning collection of various research projects and various tools that you've used, and that are available to heritage scientists. And to conclude this particular webinar, I would just like to invite everyone to tune in again in a month's time, more specifically on April the 5th, at exactly the same time, so that's 3 p.m. CET, where our very own Dr. Jana Striova is going to introduce us to a related topic to what you were presenting today, Nicola, i.e. to hyperspectral and multispectral imaging in heritage science. Thank you very much, everyone, for attending today.
Thank you.